called Introduction to Sample Distribution Central Limit Theorem, or just CLT. Okay, it looks something like this. Okay, so, there's a website, believe it or not, called random.org. And at that website, they have a pretty good description of the difficulties in really creating random selections, random numbers. You, as humans, it's impossible for you to do anything random, right? You'll have some sort of bias, left-handed, right-handed, some other bias, some visual bias, some you have a bad stomach, and when you're picking the third, your stomach will rumble when you're picking the third item or something like that. It's impossible for you to effectively pick something that's random. So you have to depend on someone else to generate random sampling for you. Okay, and that can be as simple as generating a table with numbers in it, right? Because if you assign sample numbers to your population, everybody in your population, for instance, the US government assigns everybody a number, they call it Social Security number, and you can randomly pick Social Security numbers if you just can generate random numbers, right? So we need to generate random numbers somehow or other. Computers can be programmed to generate random numbers. Usually, they really, if you think about it logically, it doesn't make sense that a computer can generate random numbers because you have to give it some algorithm, some formula to create random numbers, and that has some logic in it, so it should be predictable what numbers it's going to pick based on that. So usually what they do is they start out with something in the environment, like how fast you're clicking on the keyboard or something like that, some input in the environment that is kind of random, and then it uses that as a basis for creating random numbers. Those are called pseudo-random numbers. They're not really random, but they're pretty close. In nature, there's a lot of processes that are considered truly random. One of them, for instance, is the decay of radioactive materials. In other words, with a say uranium molecule, you can't predict exactly when the next particle is going to be released from that molecule. It's going to be random. It's not a predictable item. So you can use the decay of radioactive molecules to create tables that are random. And there's other kind of natural phenomenon like background noise, and whatever the background noise is in the solar system, in the universe that they talk about, this originated from Big Bang Theory, or background noise, electromagnetic noise from all the radio waves that are going around and stuff like that. You can generate random numbers from that as well, and from other criteria. They mentioned one in random.org, where they introduced this. They mentioned that there's a group somewhere, I guess it's got to be in California, who else would do something like this, that generates random numbers based on the movement of the fluids in a lava lamp. So you can imagine that a lot of people use different ways to do this. Okay, well, we're going to generate, in essence, eventually, at some point, somebody creates some device or some list that supposedly is random. And if you look on Blackboard, there is a file called random number table. And this is if you read through it, I guess it'll tell you exactly how this particular random number table was generated. Okay, I'm not gonna be too worried about it. It's probably pseudo random numbers generated from a computer. But all I'm concerned about is that these numbers are in essentially random order. Okay, I can at least take that assumption. Okay, so now, if you look at this, if I start right at the beginning of it, 1, 1, 1 kind of seems a little weird. 3 ones in a row, 6, 4, 3, 6, 8. But you really can't just look at that and say there's a pattern, because if it's truly random, that that could happen. Now, you don't have to start at that point. You could literally start at any point in this table, and then from there on, just use those numbers as random numbers to select your subjects in your sample, right? So what we're going to do is we're going to take another file here, which is called population of 100. So I want to take, this is an entire population. It's only got 100 people in it, but I can call it a population for argument's sake. If we had like 3 hours to do this, I might have put up a population of 50,000 up here on on the in this Excel file. But I just took a population of 100. Okay, these are, believe it or not, there's a function in Excel where you can generate normally distributed numbers, starting from 0 to 100 or from and so on and so forth with a certain mean. So that's what I did. And this is a bunch of numbers from a population. I'm going to find the mean, average. Whoops. Equals average, parentheses, and I'm going to take the average of all of these numbers. So the average of this population is 50. Now I'm going to take the standard deviation. And the standard deviation for this entire population is 9. Okay? It's actually, if I were to reformat these cells, you'll notice that it's really 9.1, right? So it's not exactly 50, not exactly 9.1, right? But it's pretty close to 9. Okay, so that's for the population. Now, we normally never know these numbers. We never know what the true mean and the true standard deviation of a population is, because the only way to know it is to measure everybody, right? And we generally don't have the resource, unless it's a small population like this, we don't have the resources to do that in Sheffield. So we're almost always working with a sample from a population. It could be a small sample, randomly sample 10 people. It could be a large sample, randomly sample 100 people. It could be a very large sample, randomly sample thousands of people, say from the population of the entire United States, right? So sample sizes can vary, but they're never the whole population. So we never really know what the mean or standard deviation of the whole population is. We do know, remember we looked at those histograms before? We do know that if we take a random sample from this population and we create a histogram from that sample, it has roughly the same mean. It approximates the mean of the population, and it also approximates the spread of the population. It'll also have a mean of roughly 50 and a standard deviation of roughly 9, because it just represents the population. We're literally picking people out of this big population, making a smaller population and calculating it, right? So, but the interesting thing about this is that if we take a look a little further, right? Some of the time, if we have this sample here where the mean is 50, if I take a sample, I'm going to have to be extraordinarily lucky for that sample to have a mean of exactly 50, right? If you can imagine, if let's say if the mean blood pressure of everybody in the United States is 80, and I randomly sample 10 people, what are the odds that I'm going to get a mean for those 10 people of exactly 80? Not very good, right? But if I do it, let's say I get 79. Yeah, I'm in pretty good shape. Well, let's say I do it again. If I do it again, there's going to be sampling variation. I'm sampling 10 other random people. It's not going to come up 79 again. Maybe it'll come up 82. Maybe the average, if I do it again, will come up 78. Maybe if I do it again, will come up 81, and so on. But if you can imagine, if the mean for the entire population, in this case 50, in case of blood pressure 80, is that number, if that's the mean for the entire population, if you take a sample, 50% of the time it's going to wind up below the mean, the true population mean. 50% of the time it's going to come up above the population mean, right? Only because that's the way that you would expect it to distribute by chance, right? So 50% of the time it could go either way. The other thing that you would reason is that for me to take a sample from a population and get a value that's very different from the population mean, if I take a sample, the mean of the sample being very different, you wouldn't expect that to happen as often as getting a value that's close to the population mean. And in fact, you'd expect a sample mean to be, the further away you get from the population mean, you'd expect to get that result less and less frequently from when you take a sample, right? So if I were to take a sample from this population, which we're going to do right now, we're going to take a sample of size 9. Okay, and the way we're going to do it, you'll notice that we have rows 0 through 9 and columns 0 through 9. If you start anywhere in this table, we're going to randomly sample this table. So if I just pick out this spot and sample it, I'd say that that's row 3, column 0. So what's in row 3, column 0? Row 3, column 0 is 52. I'm going to take 9 numbers, randomly sampled, and then you might want to continue. The next one might be row 6, column 9, row 7, column 4, row 4, column 8, so on and so forth. So I'm going to ask you guys to take your fingers out, start working. Right? Take 9 samples from this population, random samples from this population. If you don't have, if you don't have your computers up and so on and so forth, I'll be perfectly happy if you, as best you can, take a random sample visually. Okay, so I'll let you cheat, right? That is cheating because, like I said, you really can't, it really won't work, right? So, and when you come up with a mean, let me know what you get for your sample of size 9. Okay, I'll give you a minute or two, a couple of minutes to do that. What's that? You know what I mean? You know what I'm looking for, right, guys? Right. I'll do it here right now myself. Okay, I'm going to start from here, 9-1. 91, row 9, column 1 is 46. Row 1, column 9 is 37. Row 7, column 4, 0, 1, 2, 3, 4 is 41. 80 is 54. 39. 39 is 55. I lost track where I was. Where was I? I'm going to start again somewhere else. 55. 32. 24. It's 45. 47. Is 60. How many I got? I got 8. I need one more. 47 and 06 is 58. Okay, I picked out, I took a random sample of 9 individuals from this population. I'm going to find the average, the mean for these 9 people. So my mean, my average for my sample of 9 is 48. I'm off by 2, not bad, right? Okay, so I want to get a few from you guys. Okay, I got 48. Anybody else have a mean to give me? 52. Anybody else? What's that? No, no. Why would that happen? Right? It's all going to be different. Right? It's going to be. It's more often. More often, we're going to be close to 50 most of the time. But every once in a while, you got to be further and further away. But further and further away is rare because you would have to get 9 people who are way under the mean. Okay. Anybody else? 50. Okay. I need a few more. 54. 49. 52. 50. 49. I think I'm okay with that. Okay. All right. So what do you think the mean? If I were to take these samples, these sample means, and now I would create a new distribution that's not the population values, but these means of the same size taken over and over again. What do you think the average would be? Right? This is a new distribution of sample means from this population. What do you think the average would be? The average would probably mimic the average of the population, right? So you can see here, sometimes you're getting a number lower, sometimes you're getting a number higher, right? But again, most of the time it's close to 50. Occasionally it's pretty far away, but not as often as it is close. So let's find the average. Okay, and the average of all of these is 51, right? My average for my sample means came up pretty close to what my population mean is. Okay, so if I repeatedly take samples of the same size and make a new distribution, the means are going to be similar to the population mean. Big enough samples, they're going to be the same as the population mean. Okay, now what do you think is going to happen to the variability though? Is the variability going to be the same, smaller, or bigger than the population? What's that? Smaller, right? You would expect the numbers to be closer together. The population, we got people going from 30 to 72 or something like that. We're not getting that kind of variability here. So I'm going to find out what the standard deviation of these sample means is. And as it turns out, it's equal to 2. Actually, it's a bit bigger problem. I could figure that. This is a quick guess at this. But if we take a large enough sample, what we would, if we took enough samples and a large enough sample size, what we would find is that there's a relationship between the standard deviation spread of the population and the standard deviation or spread of the repeated samples of that size. So let's see what that's going to be. The sample mean is going to mimic the population mean. It's going to be close to the population mean. But the sample distribution standard deviation is going to be the standard deviation of the population divided by the square root of the sample size. So what would that be? That would be 9.1 divided by the square root of 9, which is 3. So we would expect that if we took a big enough samples, that our standard deviation would be equal to 3. In this case, we found something a little bit smaller, but you get the idea here. The larger the sample size is, the smaller the variability in the repeated samples. Why is that important? That's important because this gives us an understanding of how samples relate to the population that you're taking the sample from, particularly with regard to the sample size. So that's something we may be able to use. Okay, let's take a look at how we might be able to use that. So I'm going to put this away. And I'm going to go back to that document. By the way, the random.org site is pretty interesting. You might want to give that a try. There's a little tab at the end that says learning about randomness or something like that. That's where you want to go to like find some of this information. Okay, so I'm going to go back to that document. Where is it? Oh, yeah, that's the same one. Okay. So just to get us in the mood for this, I'm going to go back over some of the things that we understood about normal distribution. Okay, and we're going to do a couple of quick calculations that go back a step to what we were doing previously. Oops. Let me get this out of the way. Okay, total cholesterol values for a certain population are approximately normal with a mean of 200 milligrams per 100 milligrams and the standard deviation milligrams per 100 milliliters. Standard deviation of 20 milligrams per 100 milliliters. 200 average, standard deviation of 20. I'm going to sketch that out. Okay, normally distributed population. Average is 200, that's mu, right? It's a parameter of population average, 200. And the standard deviation, sigma, is equal to 20. Okay, so if I randomly select someone from this population, what's the probability that that person will have a cholesterol less than 200? 50%, right? Because half of it is symmetrical, half of it's going to be below. Okay, so let's see what the first question is. That might even be the first question for all I know. Okay. No, actually, it goes a little bit further than that. What's the probability of having a randomly second person has a cholesterol between 180 and 220? Okay, let's see. 180 and 220. Okay. If I don't need to be exact, right? What can you tell me about that? How many standard deviations from the mean is 180 and 220? One in each direction, right? We have the empirical rule. What is that? What is this area here then, roughly? 68%, right? Roughly 68%, right? So what's the probability of picking an individual from this population that's between 180 and 220? 68%. Okay. How about between 160 and 240? Right, bingo, 95, because that's two standard deviations above and below. Keep in mind, this is an approximation, right? The standard normal distribution, the empirical rule is an approximation, okay? And how about greater than 225 milligrams? Okay, well, now we got a little bit of a problem, right? We're looking for this area here, greater than 225, right? Well, it's not an even number standard deviation, so we have to use the z-score. We have to just calculate the z-score. Z is equal to the difference between the value, 225, and the mean, over the standard deviation. So that's 225 minus 200 over 20, which is equal to 25 over 20 plus 25 over 20. So that's equal to 1.25, 1.25, right? 1.25. So that's the z-score. So how do I know what the probability of selecting someone that's above that value is? Well, we got to go to our z-table. Okay, and where's my z-table? I'll take this one. You can use the one in your, this almost identical to the one in your informed. Obviously, the numbers are identical, but the format's almost identical to the one in the textbook. So 1.25, 1.201234. That represents an area of 89.44. But what area does that represent? That's the area from that z-score to the left, right? So that's not really what we're looking for, right? This from here down is 0.8944. So the area we're interested in is going to be 1 minus 0.8944 or 0.1056, I guess, something like that. All right, so so it's about 10.5% that area. Okay, let's do one more like this. Where'd it go? Here it is. Oh, no, that's the wrong one. And less than 150. I'll do the last one I'm going to do. I don't want to beat this to death because we did this before and I want to move on. Less than 150. Okay. So if this is 150, so less than 150 would be a z equal to 150 minus 225, but minus 200 over sigma. That's equal to over 20. That's equal to minus 50 over 20, right? And that's equal to negative 2.5. All right, well, negative 2.5, let's see whether that z-score takes us. Negative 2.5, 2.50 is 0.006, right? It's less than 1%. And since we're looking at less than that, we're going to talk about that area being 0.006, which, okay, didn't quite draw it quite that way, but that's what it turns out to be. And if I'm interested in any area in between, I can kind of manipulate this to get the area between 150 and 225, because I know this is 89 and this is 0.066, and I can subtract this from this and get the area between them and so on and so forth. We played around with that quite a bit. Let's take the next step now. Okay. Okay, now let's say we take a sample of size 25 from the population I just described. Okay, what's the probability that the mean of the sample, that if we take a sample of size 25 from this population, what's the probability that the mean of the sample is larger than 204? Well, I'm looking for the mean of the sample. I'm looking for probability mean of the sample. So what I need to understand is what is the distribution of repeated samples of size 25 look like. Okay, so I'm going to go back here. I'm going to start a new page. Okay. Okay, here was our population. Our population distribution was a mean of 200 and a standard deviation of 20. So two standard deviations was 160 below and two standard deviations above was 240. Let's take a look if we take repeated samples from this. If we take repeated samples, our mean, our expected mean is going to average, if I make a new distribution, which represents repeated samples of size 25 from this distribution, from this population, what is that going to look like? Well, the mean, I'm going to call it X bar. The mean should approximate the mean of the population, 20, half the time, 200. Half the time, we'll get values for that average of 25 that are below 200. Half the time, we'll get them above 200. Now, the only thing is now, since each one of these values is going to be smaller, it's going to be closer to the mean, the variability is going to be different. So what is our standard deviation for our repeated samples of size 25 going to look like? Right, that's size 25. What is our standard deviation going to look like? Okay, it's going to be equal to the standard deviation of the population over the square root of the sample size. Right, so what is that? That's 20 divided by the square root of 25 is 5. That's going to be equal to 4. So repeated samples is going to have a mean of 200, right, of that sample size. And two standard deviations now is going to be, two standard deviations to the left of that is going to be, well, 196, 192, and 208. So 95% of the samples that I would take of size 25 should fall between 192 and 208, right? A lot narrower than our population spread. So let's go back to that question. What's the probability that we would find a sample that's larger than 204? Sample mean larger than 204 if we took one sample of size 25. Well, this is the distribution of all the possible samples of size 25. What's the probability that we would get a value for our mean that's greater, right? That's greater than, what did I say? 204? Okay, 204. Okay, 204. Well, for starters, the standard deviation for the sample distribution is 4, so I could use the empirical rule if I wanted to do it, right? Okay. So 4 and below, 4 above, that's 68%. That's going to leave 34 and 34. That's going to leave 16% here. So probability is 16%. Okay. So let's go back here. What's the probability to get a sample mean between 192 and 204? Excuse me. 190. Thank you. 192 and 204. Well, this end here, right? That was one standard deviation above the mean. Now this is two standard deviations below the mean, right? So let's think about it. What's that going to mean to me? Well, if that's 16% in there, and this is 95%, I know that this little tail down here is going to contain about 2.5%. So I have 16% accounted for here, 2.5% accounted for here. So in between, I would have 100 minus 2.5 and 16, or 18.5%, right? So it would be 81.5%. Would be between 192 and 208. You can play this back later on if I'm going. I'm kind of purposely rushing this a little bit. You can always play it back later on. But you see the idea here. We're learning that there's a predictable relationship between a population and a sample of a particular size. Because if we did it repeatedly over and over again, we know how it would behave. So we can understand the probability of where it's going to land in terms of like the population mean and spread. Okay, so let's go back here. If a sample size of 100 is taken from this population, what range would we expect 95% of the sample means to fall in? I'm going to close this. Okay, so here's my sample distribution. Right? X bar is saying is going to be 200. And standard deviation, what's the standard deviation is going to be equal to? We have a sample size of 100. It's equal to sigma over the square root of the sample size, right? So if sigma was 20 over the square root of the sample size, 10, so that's equal to 2, right? Okay, good. So the standard deviation is equal to 2. What range of values would we expect for sample sizes of 100 if we took them? 95% of the results that we would get if we repeatedly took samples of size 100 would fall between 2 standard deviations below the mean and 2 standard deviations above the mean. So we would expect 95% of the time we'd get a result between 190, 196 and 204. Right? Narrower again because of the larger sample size. Good. So now that we have that, let's take a little bit of a closer look here. Okay, really 95%, right? The empirical rule let me call this an approximation. It let me call this a value, a z-score of, what did it call it? What z-score did I use? I used -2 to +2, right? So I said to myself, well, that leaves 95% between these two z-scores, which means there's 2.5% here and 2.5% here, right? Let's go to the z-table and find out if that's really true. If I go to the z-table and I look up, I'm going to look up at the lower end here because it's going to be a little easier. If I look up what the z-score is for 2.5%, in other words, only 2.5% left in this tail, it should be a value of 2, right? So I'm going to go down here and take a look at the z-score 2.00. Well, it's not 2.5%, right? It's a little less than 2.5%, right? It's 2.28%. 0.0228. So again, the empirical rule apparently, or now it's clear, it really is an approximation. What really is the z-score that gives you 95% between that below the mean and above the mean? So the way I'm going to find that is I'm going to look at the areas instead and look for an area that equals 2.5%, right? Just like we did on the exam. 2.5%. Let's see, 2.5. Here we go, right here. Right? Can you see it there? Can you see it from the right? Where'd it go? There it is, right there. And what value is that? That's 1.96, right? 1.96. So really, 95% of the sample results would be between 1.96 standard deviations below the mean and 1.96 standard deviations above the mean. Okay, so that's what we're looking at there. Okay, so we're going to take the next step now, and that is we're going to take a little bit of a leap of faith here. So, so if I knew the population mean was 200, and I were to say to you that I'm going to take a sample of size 100, you would tell me, you know, there's a 95% chance that the sample result you get is going to be between 2 standard deviations below the mean and 2 standard deviations above the mean. Standard deviations being equal to sigma over the square root of n, right? You want to know something? It's very inconvenient to call sigma the standard deviation for the population, then use standard deviation here. I'm going to use another word for standard deviation, another phrase. I'm going to call that the standard error instead of standard deviation. So from now on, if you see standard deviation, standard error, you know I'm talking about the sample distribution, not the population distribution. just to make things simple. So I could say, if I knew what the population mean was, I could say I'm 95% certain that based on the sample size, that I will get a sample result, a sample mean between negative 1.96 standard deviations below the mean and plus 1.96 standard deviations above the mean. I would expect to get that result. Let's flip that around a little bit. Let's say we don't know what the population mean is, right? Which is the case, we never know what the population mean is, so we don't have to imagine it. That's the truth, right? That's the one part of this whole thing that I've told you so far that's always going to be universally true. We don't know what the population mean is. Let's flip that around, and this time I'm going to say, if I take a sample mean and it comes out to be, let's say it comes out to be 203. I'm 95% certain that sample mean is within 2 standard deviations of the population. Oh my goodness. Well, you know what that makes me, that means that I could say that if I take that 203, instead of like centering it on the population mean, I take that 203 and I say to myself, well, how far is 2 standard deviations above here, really 1.96, and 2 standard deviations below here? Well, if the first part was true, that I could predict whether or not I'd be within 95% time, I'd be this close to the population mean, then it's also true that if I take a sample, that the population mean will be within 2 standard deviations of the result that I got. So if I calculate what those values are, in other words, 203 is the sample mean that I got for a sample size of 100. Now I'm going to say to myself, I'm going to take that 203, my X bar, and I'm going to add and subtract from that X bar 2 standard deviations, or really 1.96 times the standard error, right? Standard error happens to be, what do we say it was, 4 or 2? 2. 1.96 times 2, I'm taking the standard error, 2, and I'm going to add and subtract that from that. Okay, so let's see, what does that turn out to be? So it turns out to be 203 plus or minus 1.96 times 2 is going to be 3.92. So that's going to be, 196.08 to 203.92. I can say that I'm 95% certain that the true population mean is between these two numbers, for the same reason that that if I knew the population mean, I could say my next result of sample size 100 is going to be within 2 standard deviations. Are you guys comfortable with that? Well, what does that do for us? What does that do for us? Let's see what that does for us. That tells us that if I find out what X bar is, like in this case, I said X bar is 203. If I just did a sample size of 100 and found the mean to be 203, I'm stuck out in the wilderness here. I can't say to you how well I know that, how close. I can't say, oh, I'm within 3 of the mean or within 2 of the mean. Up until now, I couldn't tell you how well I knew how close I was to the population. And I still really can't. But what I can tell you now is that I'm 95% sure I'm within that range of the mean. The mean is between those two numbers. Am I 100% sure? No. But I am 95% sure. Yes. I'm sorry. I did it wrong, didn't I? I said I called the mean 200. You're right. 203. That should have been 203. And this would be 199.08 to 206.92. Right? Yeah, you got it. Right. Exactly. That's what happens when you get old. And Levi's getting there too because he didn't notice it. Okay. So at any rate, you get my point. Where before we could not express how certain we are of how close we are to the mean, now we have a mechanism of describing what our level of certainty is about where the mean is, right? Well, what does that mean? That means from now on, when you report, I gotta close that first. From now on, when you do a study and you take a sample and you report that the blood lead level of children in the Bronx is an average of 3.92 micrograms per deciliter, when you report, you're also going to include, well, that's what I got for my sample mean, but I'm 95% sure it's between 2.1 and say 5.7, right? So that confidence in that interval is called a confidence interval. If I use 1.96 to describe that confidence interval, that's a 95% confidence interval. Yes. That's a really good question. And you want to know something, what's the only place we can get an estimate of what the population standard deviation is? From the sample, right? We're not going to look at this week because that injects an extra level of uncertainty. So for this week alone, we're going to assume that we know the population standard deviation. And next week, we're going to see how we're going to compensate for that level of uncertainty. Okay? So let's say I wanted to be, 95% certain wasn't good enough. I wanted to be 99% certain. Right? What would I do? Well, first of all, let me ask you this. The true population, remember a sample of 203? Let's say for argument's sake, my confidence interval was 201 to 205, right? Okay. If I wanted to be more confident, would I make my confidence interval wider or narrower? Think about that for a second. I want to be more confident that I captured the true population. Make it wider, right? If I'm willing to be less confident, what would I do with it? Make it narrow. I could afford to make it narrower. If I'm willing to be, let's say, only 90% confident instead of 95% confident. Let's say I need to be 99% confident. In other words, if I go back to my sample distribution, I want to be 99% certain that I captured the population mean. So how much can I have in each tail if I'm 99%, if I want to be 99%? Right? 0.5%, 0.005. 0.005. So in my formula, X bar plus or minus the Z-score times the standard error for 95% confidence interval, we know we use 1.95. For a 99% confidence interval, well, let's see what Z-score we have to have only 0.05, half of 1% in that tail. 0.005. 0.005. Let's see. 0.052, 0.051, 0.49. I'm going to go with 0.49 here. You use either one of these two. Turns out a little closer to this one. So what is that Z-score for 0.005? It's going to be 2.58. So instead of using 1.96, I'm going to use, for my Z-score, 2.58. So now, because I'm multiplying my standard error, whatever it happened to turn out to be before it turned out to be 2, instead of multiplying by 1.96, now I'm multiplying it by 2.58. So now I have a wider confidence interval. I can say that I'm 99% confident that the true mean is between these two values. Right? What if I'm less confident? I'm willing to be less confident, but I want a narrower range. 90%. I can go back to 90%. If I look it up in a table, it's going to be 1.64. Right? So all you need to do is remember those numbers for now. If you know what the standard deviation of the population is, you can use those numbers to determine what level of confidence that you have for the true range for the population. Yes. More confident is wider. In other words, the idea here is you want to be able to say that the true mean is, you'll never know what the true mean is, but you want to be able to express a level of confidence that you've captured the true mean. So the wider you make it, the more confident you can be, 99%. So a bigger z-score gives you a wider range. By the way, you're adding and subtracting this z times the standard error. A lot of times, since you're adding and subtracting that, it's kind of like something called the margin of error. And that's in fact what we call that, the margin of error. Okay, that's z times standard error. So if that z is small, the standard error stays the same because that's based on the population, standard deviation, and sample size. But that z-score, if you make it a smaller number, it's going to be a narrower range, smaller margin of error. If you make it a bigger number, it's going to be a bigger range and more confidence that you have captured the mix. Let's try one example of this, or maybe we can even get away with even more one example. I don't like that one. Yeah, let's see. I don't want to do that one. I'll do this one with the detergents. You sample 100 bottles of detergent, not exactly a public health problem, right? And find that on average, each bottle would be sufficient for 57 washing loads. You know the standard deviation for the entire production of 100,000 bottles is 5 loads per bottle. That's a little bit of a kludge here because we're saying we know the population standard deviation. So ignore the fact that it's detergents has nothing to do with public health. And let's see what we can do with this. I'm gonna sketch this out, and then you guys can maybe do some of these solutions. Okay, the mean was 50. The mean of our sample was 57. Right, the mean was 57. The standard deviation sigma for the entire population was 5, and our 5, and our sample size was 100. Okay. But first of all, is 57 mu or x bar? Is it a parameter or a statistic? 57. How did we get to 57? We sampled 100 bottles, right? So that's x bar. That's a statistic, right? And is 5? Is that sigma or standard deviation? That's sigma. We defined it as sigma, right? Okay. Calculate the standard error for repeated samples from this population of size 100. Okay, so what's the standard error equal to? Anybody remember? I know it's been a long time, like 40 seconds since we said this. What's that? Okay, so what is it? Let's square root of 10. 10, right? 0.5, right? Okay, good. That's the standard error, right? Okay, so now what's the next step? Okay, calculate standard error. Calculate the 95% confidence interval for the true population mean based on this sample. Guys, remember the formula? X bar plus or minus. Well, if we want a 95% confidence interval, what am I going to use for the z-score? 1.96 times my standard error, which is 0.5, right? So you guys tell me, what does that turn out to be? I'm going to write the formula out just there so we know what it is. That's z for 95, or alpha is equal to 0.05, in other words, a 5% error, times 0.5, times standard error. Okay, this is the formula. This is substituting for the values. What was that, 57? Plus or minus 1.95, 96.5. Okay, so what's the result here? What's the low? What does this turn out to be? 1.96 times 0.5. 0.98. So our margin of error is 0.98. Right? So the upper limit is going to be easy. I'm just going to add it to 57.98. And the lower limit is going to be 56.02. 56.02, comma. Okay, so if you were to describe this, we would say we got a sample mean of 57 with a 95% confidence interval of 56.02 to 57.98. So what do we expect to find within that range? 56 to 57, 58? What are we expecting to find within that range of 56 to 58? The true population mean, right? How certain are we that we're going to find it in there? Right, and if I wanted to be 99% certain, what's the one thing I would change here? The one, what would I use instead of the 1.96? The other one, okay, 2.58. Okay, by the way, by the time we're done with this, you're going to remember all these numbers: 1.64, 1.96, and 2.58. Okay, that's for a 90% confidence interval, a 95% confidence interval, and a 99% confidence interval. Okay? All right, so let's throw a monkey wrench into this whole thing. And we're going to finish up, we'll finish up with this. Actually, I think what time does this class end? No one knows what time this class ends? What's that? 10 up? Okay, good. We got a few minutes. Okay, I'm going to throw a monkey wrench into this whole thing and talk about proportions. Okay. So, because I think I already posted it. I posted a homework. You got some time. You got quite a bit of time to do it, so it's not like you have to get it done by next session. But it does have a problem too about proportions. So let's talk about proportions. Okay, works this. What did I do now? Did I do something wrong? One of them, I think there's two, right? Two parts? I think there's two parts. Second part is due in 2 weeks, right? Okay. So at any rate, so let's take a look at proportions. You know, by the way, don't get worried about that because, you know, it's not like, you know, carved in stone. I make these dates up. So it's not like I can't change them. You know? Suppose that I don't have a lot of power around this place as an adjunct, but one thing I can do is change the date of an assignment. There, suppose that's a lot of power. Okay, suppose we want to know the true population proportion of Americans who are willing to accept a cut and living standard to help the environment. Lately, it doesn't sound like very many, right? Okay, in 2010 General Social Survey asked a random sample of Americans how willing they were to accept the covenant. Out of 1,381 respondents, 496 said that they were very willing or fairly willing. Okay, so let me write those two numbers down. Out of 1,381, 496 said yes, that they were willing to take a cut. What proportion of people said that they were willing to take a cut? Well, it's going to be 496 over 1,381. Right? And let's see what that turns out to be. And it turns out to be 35.9%, 0.359. Okay, so that's interesting, right? Okay, so you want to know something? I casually put this thing P over here for proportion. You know, just like we use mu and sigma to represent population parameters, we use P usually when we're discussing the population proportion. So to distinguish my sample proportion from the population proportion, I'm going to put a little crown on top of that. Actually, I think in typing they call that a caret, right? I'm going to put a cap, P cap, I'll call it. Right? Okay, so P cap is equal to 0.359, the proportion I measured. That's not the entire population of the United States of America, right? That's only the 1,389 people I randomly selected, presumably, right? Will I ever know what P is? No, unless I ask everybody in the United States how they feel about this. I'm never going to know what P is. So I know that my sample came out to be 0.359. I'm never going to know what my population proportion is. So as a consolation, at least I can maybe calculate how likely that how close I am to the true population proportion, right? And that's going to be based on the sample size and the variability that I would expect to get in samples like this. Okay, so we got P cap, right? So we need a standard error, right? So how am I going to calculate standard error? Well, in this case, for a proportion, it's going to be equal to the square root. You're going to have to take my word for this for now. Square root of P, the proportion, times 1 minus P over the sample size. Square root of the whole thing. That's going to be my standard error. Okay, so what is the standard error in this case? It's equal to the square root of 0.359. I'm going to do this again over here. The square root of 0.359 times the square root of 1 minus 0.359, which is 0.641. Did I get that right? It goes together, carry the 1. I think that's right. Over my sample size, which was 1,381. That's going to be my standard error. So what's that equal to? I'm going to put this in memory. I cleared it. I guess I'm not going to put it in memory. So 0.359 times 0.641 divided by 1381. Comes up with that. I'm going to take the square root of that. That's equal to 0.01. I'm going to round it off, 0.013. That's my standard error. Now, what do you guys think the formula is for calculating my confidence interval? Right? Remember what it was before? It was X bar plus or minus 1.96 for 95% confidence interval times the standard error. Well, how about now? P cap plus or minus 1.96 times my standard error. Same deal, right? So P cap is going to be, excuse me, I'm going to undo that. Can I undo that? I should be able to. Oh no, I got a spinning beach ball now. Oops, ball went away. So P cap, which is 0.359 plus or minus 1.96 times 0.013. Let's see what that turns out to be. Okay, 1.96 times 0.013 is equal to about 0.025. I'm going to round it off at 0.025 so we don't spend all night here. That's 0.359 plus or minus 0.025. So what's our 95% confidence interval? It's going to be everything out. It's going to be equal to 0.359. I'm going to put that in memory. Minus 0.025, which is equal to 0.334. 0.334. And where'd it go? Cool. Plus 0.025 is 0.384. So I'm 95% certain that the true population proportion of Americans that would be willing to take a cut in living standard to protect the environment is between 0.334 and 0.384. Right? Well, it's nice. Now I have, see, I have a way now to, even though I don't know what the true population proportion is, I have a way to describe how accurately I think I know it, how close I can come to it, right? So that's value. For instance, this also tells me that I'm 95% certain that the majority of Americans aren't willing to give up their living, reduce their living standard to protect the environment. How do I know that? Because I'm 95% sure it's not 50% or over, right? I'm 95% sure it's not above 38.4%. So now we have something even more valuable. We have a mechanism to compare two numbers, a group against one group, a sample from a population against some value we want to compare it to and know how certain we are that it's really different. Because up to this point, if we didn't know that, all we would know is that the population proportion of our sample was 35.9. We wouldn't be able to say how certain we are that the majority of Americans don't support this, but because we've been able to say that that's wrong, because that the majority, we wouldn't be able to say that the majority of Americans don't support this because we really don't know how precisely we estimated the population proportion. But now being able to calculate a confidence interval allows us to at least say with a level of certainty that 50% is outside of this range. Okay, we're going to get more sophisticated with the way that we use that. Okay, this is a little bit of a kind of a gimmick right now, but we're going to get more sophisticated in the way that we use it. See how knowing how sample distributions work allow us to draw more accurate conclusions about what we can understand and do with our sample results. Okay, so I think that's a good time to quit. Okay, any questions before we bail out? Okay, pretty interesting, right? Okay, good.